Good morning. Hola. Gonna wait for some more peeps to join up. Oh boy, we got a lot of physics for today. Let me tell you. Oh, morning. So much physics. So much physics. It's going okay. Hey class, I'll be right back. I'm gonna restart my OBS because it's looking laggy right now. My broadcasting software. BRB. Okay, class. Let's go ahead and get started. So today we did circular motion, and so what comes next sort of naturally is gravitation. So today what I'm going to be talking about is how to calculate what's called the gravitational field. But first I'm going to talk about the gravitational force, which is really just the weight force. Okay, so the formula for the gravitational force is just mg. All right, where little m, is the mass of the thing. Okay, little m is the mass of the thing, and little g is the acceleration due to gravity experienced by the thing. Oops. Okay. But in the context of today's lesson, so another word for the acceleration due to gravity another word for that is to call it the gravitational field. Okay. So the acceleration due to gravity is the same thing as the gravitational field. Okay. Now the units of acceleration due to gravity are meters per second squared. Okay. However, when we're talking about gravitational fields, we usually express the units a little bit differently, and we say that the units of gravitational field are newtons per kilogram. Okay. These two units are completely equivalent. So 1 Newton per kilogram is the same as 1 meter per second squared. So we could say that the acceleration due to gravity on the surface of the Earth is near the surface of the Earth is 9.8 meters per second squared. Or we could say the gravitational field near the surface of the Earth is 9.8 newtons per kilogram. Okay? So make sure you know this formula. I think you already do, but make sure you know that. So the main question of today is, how do we calculate the gravitational field? Okay, and so basically what we're going to do is we are going to learn how to calculate it in a couple of different scenarios. Okay, so the first scenario that we will discuss is if you just have a single point mass. Okay, a single point mass. And in that case, the gravitational field, the little g, is equal to big G times big M over r squared. Okay, so what are these things? Well, big M is the mass of the thing making the gravitational field. Okay, so in the case, if we were talking about the gravitational force experienced by us due to the Earth, big M is going to be the Earth. Little m is going to be us. Okay? All right? If we were talking about the gravitational force experienced by the Earth as it orbits the Sun, then little m would be the mass of the Earth, and big M would be the mass of the Sun. So it's all about perspective. If we were on the Moon, then little m would be our mass, and big M would be the mass of the Moon. So that's how we calculate the gravitational field due to a single point mass. R is the distance from the mass. So we can see that r is in the denominator, so the further away you get from the mass, the weaker the gravitational field becomes. That makes sense. And then big G is a constant of nature. Okay. It is 6.7 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay, it's a constant of nature. So this law is often called Newton's law of universal gravitation. Okay, Isaac Newton came up with this law. So that's for a single point mass. But most things are not points. Okay? Most things are not points. Most things are distributed objects. Okay? So the next case we are going to consider is, what if we have a spherically symmetric object? So this is an extended object, but it's an extended object in a spherical way. Okay, so a planet is an example of a spherically symmetric object. A planet is not a single point mass because it has extended, it's an extended object. But it is spherically symmetric, or approximately spherically symmetric. Okay. The sun is approximately spherically symmetric, so you could use this for the sun. And to calculate the gravitational field for a spherically symmetric object, you use what is called the Shell Theorem. And I could prove the Shell Theorem for you, but I don't really want to. It's an exercise in calculus, and I think it's maybe, if I went over the derivation, I would probably alienate most of the class except for maybe like 2 or 3 of you, so I'm just not going to go over it. But you can look it up. Look up the derivation of the Shell theorem. And what it says is that if you have a spherically symmetric object, okay, the gravitational field is going to be equal to G m over r squared. So the exact same formula, where r is the distance from the center. Okay? And m is the mass below you. Okay, so what do I mean by that? Okay. So what if I had the Earth? Here's the Earth, for example. And what if you dug a hole in the Earth so that it goes down to here? It's a really small hole, so it doesn't break the spherical symmetry. It's too negligible. And so you hung out right here. So you're underneath the surface of the Earth. Well, in that case, the r value would be the distance from the center. So this would be r right here. Okay. And m below would be, you're basically all of this mass that is below you. So this is, whatever that mass is, that is m below. Okay. So, yeah, that is the amount of mass that is below you. Notice that any of the mass that is above you, okay, does not contribute to the gravitational field that you experience. It's only the mass that is below you. And when I say below you, I don't mean like everything to the left of this line. I mean, you treat it like it's another planet that's below you, essentially. Okay? So this is called the Shell Theorem. Okay? Here's something really weird. What if you had a spherical shell? Okay? So it's an empty shell. It's just a spherical shell. If you were right here on the surface, you could walk on the surface. Okay? You would use Gm over r, because the mass below you is the entire mass of the shell. But what if you went inside the spherical shell? Inside the spherical shell, because all the mass is on the outside, the mass below you is 0. So there's no gravitational field inside a spherical shell. Okay? So basically, the moment you pass from inside the shell to outside the shell, or outside the shell to inside, gravity just disappears. Kind of cool. I have an interesting challenge problem to consider. Okay. So yeah, that's really weird. I wouldn't call the proof insane. It's not that bad, all things said and done, but probably for a high schooler, it's a little bit advanced. Okay, so let's apply the Shell theorem. So let's suppose a planet has a constant density. This is an example, by the way. A planet has a constant density of 5,000 kilograms per cubic meter, and radius let's say 4.1 times 10 to the 6th meters. Okay. What is the gravitational field let's say I'm tired. Let's say, what is the gravitational field 8, let's say 0.5 times 10 to the 6th meters below the surface? So we go below the surface. So, so the distance. So this is exactly like the problem I was just discussing. So you're below the surface. So you're right here. How far are you from the center of the planet? Well, in that case, the distance from the center would, that the distance all the way to the edge is 4.1 times 10 to the 6th. But we're closer than that because we're below the surface. So it's going to be 4.1 minus 0.5 times 10 to the 6th, which would be that's going to be 3.6 times 10 to the 6th meters. Okay. Now, how much mass is below the planet, or below the person? It would be all of this mass. So it's the mass contained within a sphere of this radius. So the mass below is going to be density times the volume below. All right, so that's going to be 5,000, and then times the volume, which is the volume of a sphere, which is 4/3 pi r cubed. Notice how I am not using the full radius of the planet. Okay, if I wanted to know the mass of the entire planet, I would use this. But because we're below the surface, any of this mass that is above the person does not contribute to the gravitational field. So we get the mass of the planet is 9.8, or the mass below, excuse me, is 9.8 times 10 to the 23rd kilograms. So then, if I want the gravitational field, what you do is you would then use Newton's law of universal gravitation. So it's going to be 6.7 times 10 to the negative 11 times 9.8 times 10 to the 23rd divided by 3.6 times 10 to the 6th squared. And we get 5.1 newtons per kilogram. Okay, so that's the Shell theorem. There are more advanced Shell theorem problems where, for example, the density of the planet is not constant, because in a realistic planet, as you go deeper and deeper, the density increases. So there's the highest density in the center. But so another interesting point about the Shell theorem that I wanted to point out is that if you are at the center of the planet, all the mass is above you. Okay, right? Because all the mass. So you can see as you move towards the center, the amount of mass below you gets smaller and smaller. So once you get to the center, mass below you is 0, and the gravitational field is 0. So at the center of the planet, there is no gravitational field. Why is that? It's because basically you're being pulled from all sides equally, and so the net result is nothing. Okay. So for our second way of, or I guess our third way of calculating the gravitational field is what if you have a two-dimensional array of masses. In this case, if you have a two-dimensional array of masses, you want to add the individual gravitational fields like vectors. Okay? So, let's go ahead and consider, let's do an example. And in this example, for simplicity, we are going to be in a universe where big G is equal to 1. Okay? So I don't have to come up with huge numbers for you guys. All right? And let's suppose we have a 3, 4, 5 triangle. So we have a 2 kilogram mass that's right here. We have a 1 kilogram mass that's right here. And these are separated by 3 meters. All right. And then this right here is 4 meters. And there's a spot right there. And I want to know, what is the gravitational field vector at x? Now, by the way, I should have talked about this, but the gravitational field of a spherically symmetric object always points towards the center of the object. So at all these different points, the gravitational field is pointing in to the center. It's a question. Does that mean the Earth's gravitational field, for example, maximizes at the atmosphere? Yeah, so that's a good point. The Earth's gravitational field has its largest value at the surface. Or very near the surface. Okay, so so I want to know, what is the gravitational field at x? Now, at that gravitational field at x is created by these two masses. So this mass is going to pull in that direction. So I'll call that G1. All right. And this mass is going to pull it in that direction. So I'll call that G2. All right. So let's go ahead and figure out, what is G1? Well, the magnitude of the gravitational field is going to be big G times big M over R squared times a direction vector. So this is the magnitude of the gravitational force, and then we multiply it by its direction vector. Now, we're in a universe where big G equals 1, so I have 1 times M is the mass of the thing creating the gravitational field. So this gravitational field is created by a 1 kilogram mass divided by the distance squared. So the x is 4 meters away from the 1 kilogram mass, so divided by 4 squared, which is of course 16. The direction vector is straight down. So that's going to be in the negative j direction. So the gravitational field from the first one is negative j over 16. All right. Let's think about the gravitational field due to the second mass. Okay. In this case, we have big G times big M over r squared times a direction vector. And the direction vector is a unit vector, of course. Okay. Big G is 1. The mass creating the second gravitational field is 2 kilograms. Divided by the distance squared. This is a 3, 4, 5 triangle. So this is going to be 5 squared. All right. And now the tricky part about this is the direction vector. So if I think about the direction vector goes down 4 and it goes to the left 3. So it's in the same direction as minus 3i minus 4j. All right? But the direction vector has to be a unit vector. So I have to divide by the magnitude of this, okay? I have to divide by the magnitude of that to make it a unit vector, okay? So remember, when you're making a unit vector, you get the direction right, and then after getting the direction right, you divide by the magnitude to make its length now 1, okay? So I'm going to divide by square root of 3 squared plus 4 squared, which is, of course, 5, okay? So this is going to be 2 over 25 times negative 3 over 5 I hat minus 4 over 5 j hat. All right. Now, how do I get the total gravitational field at x? Well, I need to take these two and add them together. All right. So adding those two together, this one only has a j component. All right. So I only have to add to the j component. So let me write this a little bit more completely. So this is negative 6 over 125 I hat minus 8 over 125 j hat. Okay. So the total gravitational field at x is going to be these two vectors added together, which would be minus 6 over 125 I hat minus, and then adding those two together, we get 1/16 plus 8 over 125 j hat. All right. Now, if I can turn these into decimals quite easily. So this is going to be negative 0.048 I hat minus 0.127 j hat, that many newtons per kilogram. Okay? So that is an example of how you calculate gravitational fields if you have random masses placed at different locations. Okay? We could easily extend this to 3 objects. It would just be a third. We'd have to calculate G3 as well. All right. Well, we're going to have a 2-pager. Bug, it's going to be a 2-pager. Hazel, it's going to be a 2-pager. Okay. So the last scenario in which you guys should calculate the gravitational field is if you have an extended object. I'm going to say an extended linear object. Okay. So here's an example. Okay. What if I want to know the gravitational field right here? All right. And I have a line. So this is a linear object that extends from 0 meters to 7 meters. All right. And so in this case, what we need to know is we need to know what's called the linear mass density. Okay. And so the linear mass density is denoted by lambda. And lambda is equal to the change in mass per change in x. The change in total mass per change in x. Okay. So the units of linear mass density are going to be kilograms per meter. All right. And the linear mass density may be constant. It might not be constant. Okay. So we're going to have a non-constant. And by the way, this is x equals 0. Okay. Maybe I should just call this point A. That's point A. So this would be x equals 7. And then we'll say that A is at x equals minus 5. All right? And let's suppose that the linear mass density is a function of x. Maybe it's a linear function of x. So maybe it's equal to 4x is the linear mass density. So what does that mean? It means that at x equals 0, the density is 0. And the density gets bigger and bigger as we move to the right. So it's kind of like it starts out really not dense, and then it starts to get more and more dense as we get to the right side. Okay, the maximum density would be 28 kilograms per meter at the right side. Okay, so what we want to do is we want to calculate the gravitational field at A. Obviously, that gravitational field is going to point to the right because it's going to be pulled directly towards the object. And so how you do this is you use integration. Okay, so what you do is you do the integral of big G times dm over r squared. Okay. Okay, so how do we do that? Well, what does dm mean? If we take lambda equals dm dx, then if we multiply both sides by dx, we get dm equals lambda dx. So in this case, dm is 4x dx. All right. Let's do this problem in a universe where big G equals 1. Okay. Now, so this is what dm means. Okay. R is the distance of x from the point A. So let's suppose we were right here at x equals 7. How far is x equals 7 meters from x equals minus 5 meters? It would be 12 meters away. All right. How How far is x equals 0 from x equals minus 5 meters? It's 5 meters away. So if you think about sort of the pattern there, r, which is the distance of point A from x, is going to be x plus 5. Okay? How do I know that? Because I just tried two values, okay? I know that x equals 0 is 5 meters away from A, and I know x equals 7 is 12 meters away from A. So this works at those 2 points, so it's got to work for all the points. So then what we do is we just plug in. Like that. So the gravitational field at point A is going to be the integral of 4x dx over x plus 5 quantity squared. Okay. Now, what are the limits of integration? The limits of integration are the x values that this extended object goes between. Okay. So this extended line of mass goes from x equals 0 to x equals 7. So my limits of integration are x equals 0 to x equals 7. Okay? So you would just do this integral. Let me show you how, if you are a noob to calculus, let me show you how you could do that. So I'm going to actually, I'm going to go ahead and share my desktop. So let's go to Wolfram Alpha. And let's say I wanted to do that integral. So I'm just going to literally type in exactly what I told you guys. So I want to integrate (4x) over x plus 5 squared from x equals 0 to x equals 7. All right, it does that for me. And so you can see that we get 1.1685. All right. Just writing that down. Okay, so our answer in this case, so you can do this even if you don't know integration. Okay, you just go to Wolfram Alpha, type it in, it'll do it for you. Like that. But you do need to know how to set it up. All right, so that is my lesson for today. We have learned 4 different ways of computing the gravitational field. We learned how to do it for a single point mass, for an extended spherical mass, for multiple point masses, and for an extended linear object. Okay? So these are some different scenarios where it's useful to calculate gravitational fields. I will see you in the Zoom room.